Hey guys, today we're going to go through lesson 3.3 about logarithmic functions. Your goal for today is to try not to think about all the food you're going to eat this week, my goal as well, so that we can learn a little bit about functions, logarithmic functions. So what is a logarithm? Hopefully you've started by watching the logarithm song video that I posted prior to this video. It's just a little goofy song to help you kind of remember this. So a logarithm is just another way of writing an exponential statement. So if you are looking at something like, 4 squared equals 16, that probably makes sense to you, hopefully. Just understand that you can write this statement using a logarithm, which is just the inverse. And the way that works is you take the base, which is 4, and you make it the base of your logarithm. And you take the outside number and you make it the inside, and you take the exponent and you put it on the other side. And so a logarithm is just representing what the exponent is equal to in an exponential function. Okay, we're going to look at the graphs also in logarithms in this section. Now, the logarithmic graph was one of your parent functions, so this should not be unfamiliar to you. A logarithm graph with any base is going to have this same shape. Now, the shape will kind of be a little bit more flat or a little steep depending on the base, but the key point and the shape of the graph will be the same no matter what the base of the logarithm is. Here, the whole point was just to show you that the exponential function and the logarithmic function are inverses of one another. And so that means that they should have a reflection across the line y equals x, which that does look like they are reflected. They also have companion points, meaning like if 0, 1 is on the exponential graph, then 1, 0 is on the logarithmic graph. It's that flipping the x and y's that you should be seeing. Okay, a couple of rules again that we saw in lesson 3.25 right before this. First off, if I have a logarithm with base anything of 1, that will always equal 0. So let me show you an example. If I say, hey, what is log base 5 of 1? You should automatically know that that is equal to 0. The reason being that if you were to change it to an exponential, anything, which in this case 5 to the 0 power always equals 1, okay? So if I ask you, let's try another one. Log base b of b will always equal 1. So log base 4 of 4. This is like me asking 4 to what power equals 4? 4 to the first power equals 4, right? So that's equal to 1. Log base b of b to the y equals y. So what's happening here, let's call it log base 3 of 3 to the 6. What's happening here is you're looking at an inverse. So the logarithm and the exponential, this is the exponential, cancel each other out. So really this logarithm, the base 3 and the 3 cancel each other out, leaving you with just 6 as your answer. So whatever the exponent is here, that'll be your answer. Again, that's because of inverses. Let's look at another. B to the log base b of something. What does that equal? So again, you have another inverse relationship where the 5 is raising to a logarithmic power. So that's an exponential canceling with a logarithm and leaving you with the 8 that is left. Okay, so these are just some properties that are going to help you with simple logarithmic operations. So a large part of your homework assignment in this section is just stuff like this. So what does this equal? And I really, really need you to try to work on solving these things by hand, not using a calculator. Make sure you know how to do it in your head, okay, for the most part. So like this question here, what's log base 2 of 8? In your head, you should be thinking 2 to what power equals 8? 2 to the third power equals 8, right? So this is equal to 3. The second one, log base 3 of radical 3. Well, I would want to be thinking 3 to what power equals radical 3. That's a little confusing, so maybe we'll rewrite it like this. 3 to the 1/2 power is the same thing as square root of 3, right? We learned that when we were reviewing exponent rules. So if we rewrite it this way, when I look at it now, I see a logarithm and an exponential combined into 1. And remember that there's a rule that says logarithms and exponentials cancel each other out. So that means that this answer would have to be 1/2. Or you could read it like this. 3 to what power equals 3 to the 1/2? Well, it'd have to be 3 to the 1/2 power equals 3 to the 1/2. So 1/2 is your answer there. This one you may want to rewrite. I was trying to write a fraction, but it wasn't letting me write it nicely. So here's what I'm asking. Log base 5 of 1 over 25. 5 to what power equals 1/25? Well, remember, negative exponents create fractions. So it's got to be a negative. And then obviously this isn't just a 5 on the bottom, it's a 25. So I would have to raise this to the second power to get 25. So this is going to be -2. 5 to the negative second power is equal to 1 over 25. So that's the reasoning there. Okay? Log base 7 of 7. So the question is 7 to what power equals 7? Wouldn't that just be 1? That would just be 1. Okay? Last one, you have a logarithm and an exponential, and the base of the logarithm is the same as the base of the exponential. So those two things are going to cancel each other out and leave you with just 11. Okay, I think I mentioned this in the last lesson, but common logarithms are logarithms with a base of 10. And in a common logarithm, the 10 will not always be given. It might just be like there's no base here. If you don't have a base written, then you need to understand that it's implied that that's a base 10. So this means log base 10 of 100. And that is something you can compute in your head because all you need to do is think 10 to what power equals 100. Wouldn't that be 2? 10 to the second power equals 100. Okay, so really the point of all these questions is just, hey, if you don't see a base, it's 10. That's what I'm trying to get at here. I think I'm going to rewrite this one, the radical, as 10 to the 1/2 power. So let's see if you remember the rule here. If I have a log base 10 and an exponential also with a base 10, those cancel each other out and leave you with 1/2. Okay, C, I'm going to rewrite it with a base. Again, base 10 is our common logarithm, so this would be a base 10. So 10 to the what power equals 1 over 1,000. Well, to make 10 into a fraction, it would have to be negative something. And then 10 to the what power equals 1,000. Wouldn't that be 3? So that would be -3 is the answer. The last one is, again, another property thing. So let's start with the exponent, and then we'll kind of break it down from there. Log base 6 of 6 means 6 to what power equals 6? Well, that's 1. So really, that entire logarithm exponent is just equal to 1. And so your answer is 10 to the first power equals 10. Example 3 is a quick question to see if you remember or see if you're able to use your calculator. So I want to show you real quick. Evaluate with a calculator. First of all, you're doing this with a calculator because it would be impossible to do in your head. 10 to what power equals 34.5? I don't know. It's not a nice number. So in your little red calculator, you are looking for the log button. Log is up here. that is what you're going to push. So you'll just do log of 34.5, and you'll close your parentheses, and this one is going to be 1.5, we'll call it 538. Didn't say what to round to, so that's good enough there. And that's all you have to do. So you're just practicing using your calculator. Again, your log button is right underneath the yellow button on this calculator, just LOG. So keep going. Log of 0.43 is negative 0.367. And then log of negative 3, look what happens. When I type in log of negative 3, I'm getting domain error. Log of negative 3 is domain error. Okay, let's investigate why. This is really asking me log base 10 of negative 3, which means 10 to what power equals negative 3? Is it possible to raise a number, a whole number, to a power and get a negative? Nope, it's not possible. So this one is undefined. You could also think of the graph. Let's go back and look real quick. The logarithmic graph never goes to the negative side. Like we said, it's not possible to take a number and raise it to a power and get a negative answer. So you are not going to ever have a logarithm with a negative inside of it, like this one here. So when this happens, if this is a negative number, then that answer is going to be undefined because negative numbers are not in the domain of logarithms. All right, so solve the equation. So what we're going to do is we're going to use the logarithm song. We're going to use the logarithm song, just basically just the meaning of definition of logarithms to help us solve these equations. So what I mean by that is you're going to look at the base and you're going to rewrite this as an exponential function. So you're going to say, what does this actually mean? Well, it means that 10 to the third power is equal to that x value. So then all you have to do is find 10 to the third power, which is 1,000. Okay, so x is equal to 1,000 for that one. B, we're going to rewrite it as an exponential. So if you do the logarithm song, take the base, make it the base. Take the outside, make it the exponent. Take the inside, make it the other side. So 2 to the 5th is equal to x. So we just have to figure out what 2 to the 5th power is, and that I believe is 32. So x equals 32 is your answer. All right, on to natural logarithms. So natural logarithms are what we call logarithms that have a base of e, okay? So log base e has a special name called a natural logarithm, and we can change it and call it ln, that's L, not I, ln for natural logarithm of x. Please understand that natural logarithms have all the same properties as regular logarithms, okay? Just remember that when you see ln, it means log base e, okay? So let's go through these properties and try to make some sense of them. ln, I call it ln for short. Ln of 1 is equal to 0. That's a property, meaning that it's always true. Why? Remember that ln means log base e. Okay, so I could rewrite it to try to make sense of it. And if I write it like log base e, then that means e to the what power equals 1? Wouldn't that be 0? Okay, so anytime you see ln of 1, you're going to get 0. Just like if you see log of 1, that's also 0. Second property says ln of e, natural log of e equals 1. Why is that? That's because ln or ln has a base of e. E to the what power equals e. E to the first power, okay? That's what this means over here. ln of e to the y equals y. That means log base e of e to the y. That's just that rule where a logarithm and an exponential cancel each other out. So these guys cancel each other out and leave you with whatever that y value is. Same thing for this last example. E to the ln x means e to the log base e of x. And that's just, again, saying that the exponential and the logarithm will cancel each other out, leaving you with just x. Okay? So this is just the natural logarithm application to all those logarithm properties we've been looking at. All right, evaluate the following logarithmic and exponential expressions. So this is just, we're going to apply the properties, okay? And until you get comfortable with ln, with ln, it may be helpful to rewrite it as log base e. So like this first one, I'm going to write ln means log base e. And then I think I'll also write the square root as e to the 1/2 power. And if we do that, then we can kind of apply a property. So what I see here is I see a logarithm and an exponential. They both have a base of e, so those two things should be canceling each other out, leaving us with just 1/2. Okay, on to the next. I'm going to do the same thing again. Ln of e to the 5th. Let's think about what that actually means. It means log base e of e to the 5th. I have a logarithm and an exponential again that cancel each other out and leave us with just 5. Okay? And third example, same thing again. I have an e, maybe I'll rewrite it just to show you, but this is e to the ln of 4, which is the same as e to the log base e of 4. And again, I have an exponential canceling with a logarithm, leaving us with just the 4. Okay? Calculator. So on your calculator, you saw where the log button was. There's also a button for ln. So if you look right under log, there is ln, and we're going to evaluate in the calculator, because these are things you would not be able to do in your head. So hit ln, hit 20, type in 23.5, and we're going to end up with 3.157 for that one. Next one is ln of 0.48. That's giving me negative 0.734. And then I don't even have to type in the next one. Do you remember what the rule is? You can't take a logarithm of a negative number. Think about the graph of a logarithm. Think about what a logarithm means. It's not possible. If you were to type it in, your calculator is going to tell you domain error, right? So no solution, undefined, whatever you want to call that. All right, the last thing we're going to do is we're going to work on graphs of logarithmic functions. And we're just going to kind of look at the parent function and then talk about transformations. I think you have 2 questions on your homework that are similar to these, okay? So we're going to start with just the parent function for a logarithm, and this is for a logarithm of any base. So the parent function of a logarithm has a key point at 1, 0, and kind of curves like this. And this is for a logarithm of any base. Okay, so it could be natural logarithm or it could just be a regular logarithm. The other important key feature is that logarithms have an asymptote at x equals 0, meaning the logarithm graph will never cross that dotted line. Okay, so it'll never hit 0 and it'll never go to the negative side. That's another important key characteristic. Okay, so let's fill in all of these points. So domain for this is going to be 0 to infinity, parentheses, not a bracket around the 0. Range is going to be negative infinity to infinity. Continuity means, is this graph continuous? And remind you that that means you can draw it without picking up your pencil, which is true. So it is continuous everywhere. Or you could just say continuity, is it continuous? Yes, it's continuous. Either one of those. What are the intervals of increase or decrease? Well, this graph will go up always. So this particular logarithm graph does not decrease at all, meaning it increases from x equals 0 to infinity. Does it have any symmetry? No, there's no symmetry in logarithmic graphs. It's not symmetric about the x-axis or the y-axis or whatever. Is it bounded? It's bounded. Does it ever have a point where it stops down here or up here? No, it's not bounded anywhere. It goes up and down forever, so not bounded. Extrema means, does it have a min or a max? No, it doesn't have a min or a max because it goes up forever and goes down forever. Does it have an asymptote? Yes, it has an asymptote when x is equal to 0. And then the last thing is end behavior. So that means when you look to the right and you look to the left, where does it go? Let me get this set up real quick. So the first one says the limit as x goes to infinity. So that means I'm going to look on the right side of the graph, and this arrow will continue to increase very slowly, but it will continue to increase forever. So we're going to call this infinity. That's a terrible infinity sign. Let me try again. Infinity. So on the right side of the graph goes up. What about the left side? So as x approaches negative infinity, my graph actually will go down forever. So negative infinity there. Okay, a couple more examples and then we're done. What we're doing here is we're using transformations. So we're going to look at what the transformation is, and then we're going to draw it. So this one, you see a +2 inside the parentheses. Hopefully you remember that anything on the inside is left or right. Plus means left, so we're making this graph move left 2. So we need to also graph that. You would need to remember, to graph this, you would need to remember the key point of a logarithmic function is 1, 0, and you're just going to move that point left 2 spaces. So that's going to move it to here. The shape of the graph will not change. You also will still have an asymptote. So the asymptote was right here on the y-axis. That also gets moved left 2. So now the asymptote here is at x equals 2. -2, sorry. Okay. This one's a little bit harder to pinpoint because of the way the parentheses is written. I'm actually going to rewrite this, I think. So 3 minus x would be the same as -x plus 3. Follow me? Just flip it. Which also means there's a negative that's been multiplied through this. So I'm going to actually take a negative out so I can see a little bit better what's going on. So really, there's a negative here, which is going to make this graph reflect over the y-axis. And there's a -3, which is going to make the graph go right 3 spaces. All right, let's try to make this graph here. We only have one key point to work with, right? We only have the 1, 0 as our key point. So we need to reflect it across the y-axis, which moves it to here, and then go right 3. Now, when you draw the graph, you need to also visualize that you flipped it across the y-axis. So it's not going to go up this way. It's going to flip, okay? Maybe before you draw the graph, maybe it would be helpful to also draw the asymptote. The asymptote doesn't get reflected because you can't reflect it since it's on the y-axis, but you can move it right 3. So we have an asymptote over here at x equals 3. Okay, 2 more. For this example C, the 3 in the front is going to make my graph taller. We call that a vertical stretch. Okay, now, it's going to be kind of hard to draw because our only key point is 1, 0. And I can't make that any taller because it's right on the x-axis, and the y value is what would be affected, but the y value is 0. So really all I can do is make my graph appear to be a little bit taller than before. That's the best you can do in this situation. You still do have an asymptote, by the way, at x equals 0. All right, last one. What's this going to make? What is this plus 1 going to make the graph do? Well, if it's on the outside, it should make the graph go up 1 unit. So the key point of 1, 0 will now be at 1, 1. Shape will not change at all. And the asymptote will also not change because you can't really move an asymptote up and really notice any difference, you know. So you still have an asymptote at x equals 0.